Hello and welcome back to my video lecture series. In today's video lecture, I want to work a relatively simple example involving momentum and impulse. And in this example, the idea is to determine the change in momentum, or in other words, to determine the impulse of an object given its initial and final momentum, but in two dimensions. So I have written on the board the initial momentum, which is 6.00 kilogram meters per second in the 0 degree direction, and the final momentum, which is 6.00 kilogram meters per second in the 30 degree direction. So this is an object whose magnitude of momentum has remained the same. In other words, since momentum is mass times velocity, the mass times the speed has remained the same, but the direction has changed. So we want to know what is the impulse of this object. And there's two ways to solve this, as with any two-dimensional vector problem. The first is to draw a diagram to scale, so solve it graphically or geometrically, however you want to say it. And I can sketch that quickly, but because I don't have an actual protractor and ruler that can be picked up by this little webcam, basically I'm going to sketch it and then I'm going to solve it the second way, which is actually analytically or algebraically. So the sketch it out method says that we need to have established an x-axis and a y-axis. And so we should draw out tip to tail. We want to figure out what is the impulse, which is the change in momentum, which is, of course, the final momentum minus the initial momentum. So we want to solve for the impulse. That means we should start by drawing this final momentum out. So we pick some scale, maybe 1 inch equals a kilogram meter per second. I'm going to pick an arbitrary scale and just do my best to sketch it. So initially it's in the 30 degree direction. So here finally it's in the 30 degree direction. So here is my final momentum. My initial momentum was 6 in the 0 degree direction, and I need to subtract that from the final. So subtracting is like adding the negative of, and the negative of a vector is always the vector with the direction having 180 degrees added to it. So that means that I'm starting here at the end of PF, the final, and I'm going 6 in this 180 degree direction. And so the thing that I ultimately want to find then is the resultant vector, which has to start here at the origin and end here at the end of the second thing. So here was P naught, and then this orange guy would be the impulse or the change in momentum. And so if I had the protractor and could show this with this webcam, I would basically need to take it out and measure what is this angle right here, and I would need to take a ruler and measure what is this length right here and convert that into a unit of kilogram meters per second using the scale that I've set up. So now that I've drawn it, let's see what that looks like algebraically. So algebraically, if I want to subtract these two things from each other, I need to first convert both the initial and the final from polar coordinates into Cartesian coordinates. So this initial one was entirely in the 0 degree direction, means that it's entirely in the x direction. So that's a relatively simple conversion to do, because it means it's going to be 6, which is the full magnitude, in the x direction, and 0 in the y direction. Okay, and then the second one, we're going to have to actually convert by making ourselves a little drawing. So this one says that I should go in the 30-degree direction, which is about like this. So here is the final, and it was 6 kilogram meters per second. And so it can be broken up into an x and a y. So here is the final in y. Here is the final in x. And this interior angle, theta, is also known because it's given as 30 degrees. So to get the x and y, I can just use a little bit of geometry or a little bit of trig functions. We know that sine of an angle is always opposite over hypotenuse. So if I want to solve for the opposite side from this angle, in other words, if I want to solve for the y component of the final, I can take the sine of the angle and multiply it by the hypotenuse. So this should be p final sine theta. And since theta is 30 degrees, sine of theta is going to be equal to a half. So a half times 6 gives me 3. So this part is 3.00 kilogram meters per second. And then similarly, the cosine of any angle is going to be adjacent side over hypotenuse. So if I want the adjacent side, I should take the hypotenuse and multiply it by the cosine of the angle. So this is going to be p final cosine of 30 degrees. Cosine of 30 degrees is square root 3 over 2, but I need to round off to 3 significant figures because that's how many I started with. And so by obeying the rules for significant figures, I actually end up with 3. And so this thing ends up being 5.20 kilogram meters per second. So I'm going to go ahead and write that up top so that I can erase this and use the space. This thing right here is 5.20 kilogram meters per second, comma, 3.00 kilogram meters per second. So now I have my initial and my final momentum in Cartesian. So now I can figure out what's the difference between the two. And to do that, I need to go and subtract the x's from each other, and I need to subtract the y's from each other. So in other words, I'm going to use that the x part of impulse is the final x minus the initial in x. And the y part of the impulse is going to be the final in y minus the initial in y. Okay, so if I want to figure out the x part, I have that the impulse in the x direction is 5.20 kilogram meters per second minus 6.00 kilogram meters per second. So that means that I get negative 0.80 kilogram meters per second in the x direction. And likewise in the y direction, I can subtract the initial from the final, so I get 3.00 kilogram meters per second minus 0.00 kilogram meters per second. So that's going to be equal to positive 3.00 kilogram meters per second. So now I have found the initial and final momenta in Cartesian, and now I find the impulse in Cartesian. So I can write that the total impulse is equal to the x part of the impulse, comma, y part of impulse. Okay, so from there, because I started in polar, I should convert back to polar. In other words, I should find the magnitude of the impulse and the direction of the impulse. So to do that, I can use a little bit more geometry. Basically, I have, again, my x and y's, and what I have is that the impulse goes negative 0.8 in the x direction and positive 3 in the y direction. So that means that the net impulse should be like this, not to scale. So I'm going to call the interior angle phi, because the actual angle that I want is here. Theta is with the x direction. I have Ix and I have Iy, and I want to find I. So I can use the Pythagorean theorem, which says that I squared is Ix squared plus Iy squared. So I plug in the 3 and the negative 0.8. I square both. That gets me 9.64. I take a square root, and I end up with that the magnitude of impulse is 3.10 kilogram meters per second. Then I can use that tangent of an angle is always opposite over adjacent, and here I'm just going to use magnitudes. So this would be Iy over Ix, so 3 over 0.8. And so I take an arctangent of both sides. The units, of course, cancel. Take an arctangent of both sides, and I get that phi is 75 degrees. And I have that theta and phi add together to make 180 degrees. So that means that theta must be 180 minus phi, which is 105 degrees. So that means that this impulse is 3.10 kilogram meters per second, comma, 105 degrees. So an impulse of this magnitude in this direction will change an object's momentum from 6 in the 0 degree direction to 6 in the 30 degree direction. So I think that's a wrap for today, and thanks for watching, and hope you enjoyed this, or at least found it helpful. So goodbye for now.